Good morning, students. Today I shall start the part 3 of this infrared spectroscopy. So, in previous lecture, that is in part 2 of infrared spectroscopy, we have calculated the energy value according to equation 9, which was E is equal to V plus half h nu, and this E was in terms of joules. Now, if we want to convert this energy, which is in the form of joule, into a wave number, then E must be divided by Hc, because we know that E is equal to h nu, and if we divide both sides the equation by Hc, then the left hand side becomes nu by c is equal to 1 by lambda, and that is the wave number. This becomes equal to the wave number, and hence this equation 9, when divided by Hc on both sides, we will get the energy in the form of wave number, and the unit will be per centimeter. So here this equation is divided by Hc. Also here h nu is divided by Hc. This becomes wave number. Here it is denoted by E prime, and its unit is in terms of per centimeter, and here it becomes nu by c. Let omega is used in place of nu. Then equation 9 can be written. This equation 9 can be written h into omega. So this is V plus half h omega, equation number 10. Again it is in terms of joule. But when we want to express it in terms of per centimeter, that is wave number, then this equation is also divided by Hc on the left hand side and right hand side also, and therefore it becomes E prime in terms of per centimeter unit, and this becomes V plus half omega by c, and when omega by c is represented by omega E bar, then equation 11 is obtained. E prime is equal to V plus half omega E bar. Here I have written omega, that is this omega is in the unit of per centimeter, but omega bar is per second, but omega bar is in per centimeter. Here it should be noted that even at the ground state, when vibrational energy is 0, that is in the lowest energy state, molecules have certain value of vibrational energy. If we put 0 for V in the equation 11, then 0, it becomes 0 plus half. So E0 is equal to 0 plus half omega E bar, and this is equal to half omega E bar. That is the energy of a molecule in case of rotational state, in vibrational state, the energy is not equal to 0. When we put V is equal to 0, it has certain value of energy, and that value of energy is half omega E bar, and this value is called 0 point energy. This value is called 0 point energy. Even at absolute zero of temperature, this means, what is 0 point of energy? This means that even at absolute zero of temperature, when translational and rotational motions stops, that is translational and rotational motions are absent, then vibrational motion still exists. That is, in that case, when translational and rotational motions are absent, in spite of that, vibrational motion exists, and the value of vibrational motion, vibrational energy is equal to E0 is equal to half h omega, and that is called as 0 point energy. So this is a very important term, 0 point energy. This is also asked in a short answer question, what is 0 point energy and what is the value of 0 point energy. So this is 0 point energy, and the value of 0 point energy is half omega E bar. Now we want to calculate the potential energy of the system. From equation 7, we have to calculate. From equation 7, we have to calculate potential energy. We have to calculate potential energy, and potential energy is equal to V plus half kx square, which we have already calculated. The potential energy which is calculated is equal to V plus half kx square. This is the equation which is obtained when we calculate the potential energy of the system, and this equation is actually an equation of a parabola. That is, this is a equation, is a parabola equation, and when a graph is plotted between potential energy and the bond length, then the form of the curve will be like a parabola, like this picture. The equation of parabola can be represented by y square is equal to 4ax, or x square is equal to 4ay. Here I have written only one equation, y square is equal to 4ax. This equation, which we have obtained for the potential energy, V is equal to half kx square, this can be rearranged in the form of this equation, y is equal to 4ax, like this. Here x square is equal to 2v into 1 by k, and x square is equal to 4 into v into 1 by 2k. So, in order to bring this equation in the form of equation of a parabola, we can write x square is equal to 4, 1 by 2k in the bracket, and v, that is, it is in the form of 4ax, a is equivalent to 1 by 2k. Here, the potential energy curve of a rotational energy level, rotational energy will be in the form of parabola, and if we take the different values of energy for different values of vibrational energy level, that is V is equal to 0, V is equal to 1, P is equal to 2, then we will get these type of values of energies from the same equation, E is equal to V plus half omega E bar. This is for simple harmonic motion, that is when the vibrations are according to simple harmonic motions, or simply we say that it is a harmonic oscillator. So, for V is equal to 0, the value will be equal to half omega E. For V is equal to 1, the value will be equal to 3 by 2 omega E bar. Value for V is equal to 2 will be equal to 5 by 2 omega E bar, and so on. And what will happen when adjacent transition takes place? That is, what energy is required for adjacent transition means the transitions taking place in the nearby energy levels, which is very close to one another. So, if we take a transition from the first energy level to second energy level, then this can be represented by this equation, delta E is equal to E1 minus E0, and that will be equal to the value of E1 minus the value of E0, that is 3 by 2 omega E bar minus 1 by 2 omega E bar, and that will be is equal to omega E bar. Similarly, for another adjacent transition, that is between second energy level and third energy level, here we can write E2 minus E1, and when value is put for E2 and E1, again we get the final result as omega E bar. Similarly, for E3, transition between fourth and third energy level, that is E3 minus E2, again we get omega E bar, and so on. If these results are represented in the form of pictorial diagram, we get this type of diagram. I have already discussed that the nature of the potential energy curve will be like a parabola, so it is a parabolic nature of the potential energy curve. Here on the y-axis it is potential energy, and on the x-axis it is the bond length, and these are the values of energies which are obtained
for different energy level. This is the lowest energy level, vibrational lowest energy level. V is equal to 0, then V is equal to 1, then V is equal to 2, then V is equal to 3, and then V is equal to 4. We have written the corresponding values. We have written the corresponding values of energy for V is equal to 0, V is equal to 1, V is equal to 2, V is equal to 3, and V is equal to 4, which I have calculated here. So these are the values, and the difference between two adjacent energy levels, the energy difference is omega E bar, omega E bar, omega E bar, omega E bar. That is, the energy levels are equidistant for vibrational energy levels in case of harmonic oscillator, that is, in case of simple harmonic motion oscillations. Now, this value of energy is called 0 point energy, which I have already discussed, that even at the lowest vibrational state, the vibrational energy is not 0, it has certain value of energy, and that value of energy is half omega E bar, and this is called as 0 point energy, which is very clear from this figure. Now the selection rule for simple harmonic motion. For harmonic oscillator undergoing vibrational changes, the selection rule is very simple, and that is equal to delta V is equal to plus minus 1, that is transition can take place to the energy levels which are adjacent to each other. From figure it is very clear. Here it is V is equal to 0, that is lowest vibrational energy level. Here V is equal to 1, here V is equal to 2, here V is equal to 3, and when a transition will take place in the adjacent energy level, which will be according to the selection rule. So this will be the transition from V is equal to 0 to V is equal to 1. This is also the transition, V is equal to 1 to V is equal to 0. Our selection rule is delta V is equal to plus minus 1. So this transition is for delta V is equal to plus 1, and this transition is for delta V is equal to minus 1. This is also called for absorption of energy, and this is also called emission of the energy. Here also it is absorption of the energy, here it is the emission of the energy, here it is absorption of the energy and emission of the energy. So transition can take place from energy level, one energy level to the other energy level which are adjacent to each other. Also transition can take place from upper vibrational energy level to the lower vibrational energy level which are adjacent to each other, and vice versa. That is, from lower energy level to the upper energy level and from upper energy level to the lower energy. Both transitions are possible because the selection rule is delta V is equal to plus. Now, expression for the transition from lower vibration energy level V double prime to adjacent upper vibration energy level V single prime can be represented by this figure. Suppose this is lower energy level and this is the upper energy level, that is rotational lower energy level, rotational upper energy level. According to the tradition, we represent by a single prime for upper energy level and by a double prime to the lower energy level. Let this lower energy level is V is equal to 1 and this V is equal to 2. This is not always. Here we have taken for our convenience or for example, but it is not always. It is V is equal to 1 and V is equal to 2. It is a lower energy level and it is the upper energy level. It may be V is equal to 2 and it may be V is equal to 3. It may be V is equal to 3 and it may be V is equal to 4. Then both may be adjacent to the one another. So what will happen for this transition? We will write the value of energy. Suppose this energy of this vibration energy level, upper energy level is E prime, and energy of the lower vibrational level is E double prime. So E prime is equal to this much and E double prime is equal to this much, V single prime plus half h omega, and it is V double prime plus half h omega. And if we want to know what will be the energy required for this transition, then we will have to subtract these two values, that is delta E is equal to V. Transition is taking place from lower to upper. So here the representation is like this, V double prime, arrow is given, that is transition is taking place from lower energy level to the upper energy level, and for this, for the lower energy level and upper energy level, we will get the difference between the two energies. This energy is higher than this one, therefore this is written before and this is written after. And these values are also written: V prime plus half h omega minus V double prime plus half h omega. When we take the common, this type of equation is obtained, and here plus half and minus half cancel out, and finally we get V prime minus V double prime. So according to the selection rule, this V single prime minus V double prime will be equal to 1, and if we put value 1 for this bracket term, then we get delta E is equal to h omega. If it is expressed in terms of wave number, then this equation must be divided by HC on both sides. So when this is divided by HC in both sides, this is converted into E single prime, that is in terms of the wave number. Better it is, we have to express this in terms of the wave number, and this becomes omega by C, and it is represented by omega E bar. So for harmonic oscillator, the frequency in terms of wave number of the radiation emitted or absorbed should be equal to the mechanical frequency of the vibration of the system. Thus, according to equation 12, this equation, the vibrational spectrum should consist of a single line, provided there are no accompanying rotational energy changes. If we consider that there are no rotational energy changes are taking place, then only a single line will be obtained. This line, this is called the fundamental frequency and is known as origin or band, origin or center of the band. The line for which nu bar is equal to omega E bar, this condition is fulfilled, is generally missing in the vibrational rotational spectra. This is the condition which I have obtained here, and for this what I have written, this I will explain later on when some more expressions I will derive. So this is a very important term, why line is generally missing in the vibrational rotational spectra. I will explain it in later on when some more expression I will derive. If rotational transition occurs, then a series of lines near the fundamental frequency occurs. So what happens when there are no rotational energy level changes? This is a vibrational spectrum, and we know that it is also associated with the vibrational energy change. So if there are no rotational energy change, then there will be single line, and if there will be rotational transition, then a series of lines will be obtained near the fundamental frequency, this omega E bar or nu bar. So this is the third part of infrared spectroscopy. In next part I will discuss onwards from this point. Okay, thank you.